علامة innovative interpret market.
On the 28th of September, Epic is visiting CSEM in Switzerland. Rolando Ferrini, here I come! Aha, now I have your attention. Let me explain. Our unique virtual visits to photonic leaders in Germany, UK, Spain, and Latvia have proven to be very popular. Our next visit is on Tuesday, September 28th, and we are off to Switzerland for a guided tour of the Swiss Center for Electronics and Microtechnology. You know it as CSEM. This is a private R&D company established in 1984 to help the Swiss watch industry innovate against heavy foreign competition. Fast forward to today, it has become one of the leading R&D centers for industrial research in photonics in Europe. Why am I so excited about this visit? 4 reasons: micro-optics, lasers, sensors, and camera systems. Number 1, micro-optics. If you follow the Epic activities recently, you have heard the expression the European micro-optics revolution. Switzerland has quickly established itself as one of the most influential regions in micro-optics, thanks to collaborations with some of the key companies in the sector in initiatives such as the famous Fabulous pilot line. CSEM is pushing the development of these miniaturized optical components to unprecedented levels. Number 2, laser technology. The Swiss watch industry is not about volume or about price. It's all about precision engineering. A Swiss watch is a jewel in which laser micromachining is the watchmaker's main instrument. At CSEM, they have been busy for over 37 years developing ultra-stable laser systems and processes from continuous wave all the way to femtosecond. Number 3, sensors and photonic integrated circuits. CSEM has developed advanced peak-based systems thanks to the robust packaging know-how. I am most excited about the integration of peaks with mechanical transducers for advanced hybrid sensors, such as the Nano optomechanical accelerometers for seismic applications. And 4, vision systems. As a center focused on industrial research, CSEM has mastered the development of full machine vision solutions for industrial process control, from the CMOS image sensor design all the way to embedded AI. CSEM's rising star, Rolando Ferrini, will guide us through those areas of expertise. I've already told him to prepare their different teams to answer the famous Epic question, because the goal of this visit is to start business opportunities. That explains why I'm so excited about this event. Let's dive in! Ladies and gentlemen, it is time. We've been preparing this for a while. Today, I'm Jose Pozo and I'm in Glasgow. I'm attending the Photonics conference and exhibition, and at the same time, I'm combining the online experience. Little by little, the industry has to travel. We need to visit each other, we need to meet each other, and we need to close these contacts, because believe me, it is very important to do things online, but it's also very important to keep building on this trust of bringing the community together. Today, I am visiting CSEM in Switzerland, in Neuchâtel. We are talking of one of the key areas, one of the key ecosystems of photonic innovation in Europe. And with also, I'm meeting a very good friend of mine, a very close friend of mine, a person I really trust, admire, and somehow I can say it as well, I love. I'm meeting Rolando Ferrini in CSEM Switzerland. Rolando, we are live. Good afternoon.
Good afternoon, Jose. Thank you for the nice words. I love you too.
It is great to see you. It is great to be here, at least to feel here. I would like to understand as much as possible on the next 45 minutes, how much business we can create with the Epic members. Tell us what's going to happen in the next 45 minutes.
Thank you, Jose, for the nice introduction, and thanks to the EPIC team for giving us the possibility of showing you in the next 45 minutes what CSEM can offer you in the field of photonics. So good afternoon, ladies and gentlemen. My name is Rolando Ferrini. As Jose has said, I'm working at CSEM when I'm responsible of the activities in micro nano optics and in general, steering the entire program in photonics. So as I said, in the next 45 minutes, we will walk through the activities that we have in photonics. First of all, what CSEM means. CSEM means Centre Suisse d'Électronique et Microtechnique, so Swiss Center for Electronics and Microtechnology. Why French? Because we are broadcasting from the French-speaking part of Switzerland, from the town of Neuchâtel, where the headquarters of CSEM are located. We have other sites in Switzerland, all of them, and we'll visit them virtually today, involved in photonics. So CSEM, as Jose introduced, was founded 30 years ago as an initiative of the watchmaking industry, which is pretty much strong here in the region. They wanted to have a research and development center serving the watch industry with microtechnology and electronics developments. And they founded CSEM, which is a private non-for-profit company partly funded by the Swiss government to develop these technology platforms that we transfer afterwards to the industry. So in the last 30 years, we actually expanded our portfolio. Now we offer today also nanotechnology, for example, nano optics, and we go up to systems that are flying into the space. One of our most favorite actual example is the lander Philae that in 2014 was landing on a comet in the framework of the mission Rosetta and was sending back to the Earth images from the comet. These images were taken with 7 CMOS cameras that were conceived, developed, and fabricated at CSEM. And 15 years before actually the use, they were then launched into the space. And after 15 years traveling into the space, they were still able to send images in a very reliable way. Reliability is one of the Swiss footprint of CSEM. So photonics at CSEM has a very long history. Actually, today we are broadcasting from the Observatory of Neuchâtel. It was part of the University of Neuchâtel, built in the 19th century. It was part of the department working on time and frequency since that times. Nowadays, this observatory and the activities on time and frequencies are part of CSEM, and we have here colleagues developing laser sources and laser systems for different type of applications, going beyond time and frequency. If we continue our tour of Switzerland on the activities on photonics, other old activities we have since more than 20 years, 25 years, are the activities in micro nano optics. They started actually more than 20 years ago in Zurich in the RCA lab for development of nano-optical features for security, so means passport and banknotes, that were transferred afterwards to the Porsche Institute and landed then at CSEM. So today we develop micro and nano-optical components for different types of applications, going beyond the security, going up to, for example, AR/VR, which is hot topic today. If you continue the tour, we can go eastbound, and in the east part of Switzerland, there is a valley, the Rhine Valley, which is very much known as the Photonics Valley, because there we have a lot of optics and photonics company. Most of them, they are already members of EPIC. And there we have colleagues in Landquart, in Grison, developing optical systems for life science applications and beyond. If you now fly back to Neuchâtel, we go back to an activity that we started more than 10 years ago in the development of vision systems and nowadays of multispectral imagers. And then we go to the newest activity, photonic integrated circuits, that we fabricate in our clean room facility here in Neuchâtel. It's a MEMS fab that nowadays is also used to fabricate and manufacture these photonic integrated circuits. And then I will let Amir, my colleague Amir, broadcasting from the clean room, from inside the clean room, showing you what we are doing in the domain of photonic integrated circuits. We'll fly back here afterwards to continue with the other colleagues, showing you all the other technologies that we master and we offer to our customer at CSEM. One last disclaimer. CSEM is an RTO, research and technology organization, like, for example, Fraunhofer in Germany or VTT in Finland, and so on and so forth. So our job is to develop technologies, not to produce. For sure, we can assist our customers with demos, with prototyping, with small series, piloting production, but the main aim is the transfer of the technologies to the industry. And if it's necessary, do this through our partners in the industry that can then produce the final products for our customers.
Before we go to the clean room, Rolando, first of all, we are in the observatory. And I don't know if because of the quality of the camera, we want to know what is the statue that you have behind you. It's very important.
This is Mr. Hirsch, is the guy who built the observatory back into, I think, 1850 something, 1859, if I'm not wrong, but it might be wrong.
The Hirsch Observatory, we are there, and from there we're going to go to the clean room, correct? And now we're going to talk to Amir. Pay special attention to
Can you
this.
hear me?
Amir is about to set up, Amir, you will hear you loud and clear.
Yeah.
Amir is
Can you
about to
see me
set
as
up
well?
the first pilot production there is on thin lithium niobate for ultra-fast modulation. This is a huge breakthrough for photonic integrated circuits. I want everyone in the industry, at least everyone in the EPIC network, to help, to assist this huge phenomenon. Amir, good afternoon.
Yeah, thank you so much, Jose, for the nice introduction, and good afternoon. It's been a long time. It's a long time to see you, but it's my pleasure to actually introduce our activities with regards to photonic integrated circuits at CSEM. And today I have the pleasure to actually do this where the magic happens, from the inside of the clean room. I'm actually inside the CSEM clean room. You can see. So following up to actually the nice introduction by Rolando. So photonic integrated circuit is a new activity, relatively new activity at CSEM. So here at CSEM, we try to cover a wide range of activities sort of corresponding to photonic integrated circuit, starting from designing them to fabricating them here in-house, but also measuring and packaging them, which my colleagues would sort of show the packaging activities. But last thing, our colleagues at Observatories are experts on system integration. So they are we can actually use the peaks generated at CSEM and actually make a whole system around it. But what I want to especially, sort of talk today is about a new platform we've been developing based on lithium niobate on insulator. And thanks very much, Jose, for this nice introduction. Well, lithium niobate is not a new material, so probably everybody is at some point have used lithium niobate. It's very interesting electro-optic material. It has one of the highest electro-optic modulator. It has very nice non-linearities and a wide transparency window. But the difference here is that we make thin films of lithium niobate, and we make waveguides by etching, and so then we can actually go on for complex integration. And the actually magic of this happens here. So let me show you, take this time to show you a few examples, very live.
They know how much I love watching the examples.
So this is Jose's actually an LNOI wafer, and I don't know, it's actually patterned. So we have, obviously, it's a very complex, structure. So it's like a very complex integration. So you might actually see in some angles some of the patterns. So this is a wafer at earlier stage of its, development. So it's actually, we can see this practically looks like a silicon wafer, but with a very thin film of lithium niobate. 600 nanometer.
It's lithium niobate on insulator. Basically, you have a silicon, a layer of oxide, and then you have and we are talking about an 8. Is look like a 6-inch or 8-inch wafer?
No, so that's a very good question. Our fabrication facility here at CSEM is based on 6-inch. So, and this is the largest lithium niobate wafer, LNOI wafer you can actually buy commercially. So we buy these sort of wafers, these raw wafers like SOI wafers. And our business is actually to pattern and etch and then put electrodes. I mean, I have one more example for you to show is, let's say we have one more wafer. It's kind of hard to see, but it's slightly later stage of its development. So this is right after the metallization. We haven't yet lift off the electrodes. But, so you start by patterning the waveguides, and then you go to, more and more complex, sort of steps. And once the whole thing is actually finished, I can actually show you some of the final structures. So these are some of the chips ready to be shipped to the customers. So you might actually see these longer ones, Jose, are actually some of the modulators with very V-pies below 1 volt. So we designed them to actually operate at tens of gigahertz. The ultimate sort of target is to be above 100 gigahertz. So you can see other complex structures, kind of hard to see, but yeah, so we have a variety of components, tunable resonators. You can actually see it. I mean, I have few SEMs because it's really hard to see, but yeah, this is, for example, the example of a tunable resonator we measured, actually very recently. Another of this in the form of a racetrack. But so, for example, this is a MZI. structures.
In one hand, what you have is a platform today in which you can do full photonic integration on a lithium
Exactly.
niobate. At the same time, the industry also demands lithium niobate modulators that can be incorporated to other platforms like silicon nitride and PLC.
Precisely.
Is that also also in the room? Because I have somebody in the room who would be very interested on this. I had the company Team Photonics representing in the room, actually
Yeah.
represented by Adrien Billet. Adrien, good afternoon.
Good afternoon.
So you're representing the PLC platform here, and what I always thought is that we do need to integrate on these low loss, ultra low loss stable platforms, a way to integrate modulation. How do you feel about having perhaps some kind of pilot production or lithium niobate thin modulators in Europe?
Well, it feels really good, actually. We've been in talks previously with Amin, so I'm sure we can find synergies. You know, our PLC components can be used for packaging. Maybe we can offer some functions that they don't yet have on the platform, some passive functions. And what I can say is that we get requests for modulating devices that may hybridize several platforms for sure.
Yeah,
so can you tell us? Yeah.
Jose, I've been in contact with actually Adrian for a long time, and I think their interposers are particularly this buffed interposers they are developing is particularly very interesting for us to package it, because one of the challenges in lithium niobate is actually spot size converters for fiber to chip connectors, and I think there is a lot of room for collaboration there.
What is the dimension in the lithium niobate platform, Amir? What is the dimension of a single mode waveguide at 1550?
Well, so the thickness of the films that we are working, the standard thick film is the 600 nanometer X-cut lithium niobate, and this sort of we can actually taper our structures down to around 50 nanometer, but the standard single mode low loss waveguide is 800 nanometer on top. But lithium niobate, we might actually kind of barely see it here. It when we etch it, it comes with a sort of wedge angle. So it is 800 nanometer on the top, and somewhere around a micron, like 1.1 micron at the bottom.
Okay, so definitely this is a great room for cooperation with Team Photonics. I hope you make it happen, Adrian. Thank you very much for joining.
Actually,
I'll come back to you later, Adrian. Please continue, Amir.
Yeah, so last one, let me take the last minutes of my actual time, and then maybe walk you through actually our facilities at what we have at CSEM. So this is a.
Can you tell us a bit about the size and the class of the clean room?
Yes. So we have a 600 square meter of the surface of the clean room. It's actually, I'm going to walk, it's divided in 4 zones. So thin film deposition, lithography, etching, and metrology. And this is a class 100, clean room. So originally it's actually sort of a MEMS clean room. So we have a lot of activities in trying to co-integrate MEMS and photonics in addition to this lithium niobate. But we are sort of now trying to, do more and more, photonics and nano structures inside of this clean room. And one of the interesting facts is that we can not only, we are especially in R&D, but we can also handle small scale production to around 200 wafers a year. And if I sort of continue this, Jose, so this is the region of the sort of thin film deposition for us. This is the hall for thin film deposition. We have also the equipment from LCD, sputtering, the metallization, chambers, all the dielectrics that we know, MOD, ALD. So anything actually we need for this type of operation. So this sort of hall that I was talking at the beginning, so this is our metrology region. So we have all sort of, metrology equipment that we need to characterize the process control in the middle of the steps. And remember, this is actually quite complex process. So many in north of actually 50 fabrication steps. So things like, stress control, thin film, and then SEM obviously is our eye, and sort of mechanical profiler, optical profiler, probe stations, and the tools to measure stress. So as you can see, probably very clear from the yellow eyes, this is our photolithography region. And here we have all sort of, tools that we need for photolithography, such as, mask analyzer, automatic coaters, developing machines, bonding things, and so on. And the last but not least, or let's say most important part for lithium niobate, because that's the most difficult, things about lithium niobate, is its patterning and etching of it. And this is our sort of last, zone, which is dedicated for etching. And on the right, we have all the RIE, ICP type of things, specialized tools for silicon etching, for hard materials such as lithium niobate, but also dielectric etchers, and all the liquid chemistries on the left, which actually we needed, KOH, BHF, and all
I've
the
been
other
to the
things that
clean
actually
room and I recommend everyone to have a look. But you mentioned the word metrology, and I have one of the key members in Metrology Solutions, Sensofar, represented in the room by Carlos Bermudez. Carlos, what did you see that made you interested? What kind of room for cooperation could you observe here?
Hello, good afternoon from Barcelona. Thank you, Jose, for thinking of us. Yes, we are manufacturers of optical 3D profilers. In fact, next month we are celebrating our 20 years anniversary. So it will be a big party here in Barcelona. Yes, so semiconductor is one of our fields of expertise. So we have been selling optical 3D profilers for semiconductor industry since the very beginning. So with our interferometric capabilities, we can measure sub-nanometer vertical resolution. So it's we are quite accustomed to this kind of applications.
Notice, Carlos, that the lithium niobate platform, what you're going to have very different is that the waveguide that you are used to in silicon is actually open on the sides a little bit. And metrology there is a challenge. So I think there is a particular challenge to contribute. And Sensofar, Amir, Sensofar is the best company that can help you on this challenge. Carlos, I'm going to come back to you, but now I have to go back. I have to fly back to the observatory. Amir, thank you so much. Congratulations. So much. Go lithium niobate. Amir, thank you very much. Rolando.
Thank you, Jose. It was nice to meet you again. Thank you.
Thank you very much. Thank you, Amir. So now we go to another domain, which is laser and instruments. And I just introduce you my colleague Shangun, who will bring you in this domain, in this field.
Hello.
Hello, good afternoon.
Hello, good afternoon. So it's my great pleasure to welcome you here to the Laser and Quantum Technology Group at CSEM. So today one of the most fascinating topics in optics, the photonics industry is the laser. Because the most advanced optical systems are running with at least one laser. And then the quality of the laser is the key to bring such optical system to our daily life. And over the last 10 years, our group is growing so fast and then broadening our competencies across the entire spectrum of today laser technologies. Especially our group is already well known for the generation of ultra-stable laser source and both continuous wave and femtosecond laser source. On top of this, we are also specialized in high power laser systems and also the modeling of laser physics, just to mention a few. And moreover, I'm pretty much proud to mention that most of our technologies are undergoing a transfer to our valuable industrial partners for their products. And it's amazing to see that the applications of our technology is so broad, such as atomic clock, metrology, optical sensing, optical communication, and spectroscopy, and even astronomical spectrograph. And today I have two demonstrations for you. So let me start with this sensor, which is a mid-IR gas spectrometer. Frankly speaking, this is really a masterpiece that which we integrated last year at CSM within the framework of a European project, FLARE. So there is a link. If you want more information, you can visit this website. And actually, this sensor was developed for airborne applications to monitor the air quality. And frankly speaking, building up a mock-up system, breadboarding in the laboratory is straightforward because it's not at all restricted by the space and weight and the power consumption. But when it comes to the design and implementation of such a system for a small drone, this is a totally different story because it can be realized only by professional expertise and systems engineering. So obviously the solution lies in CSEM, and then our group was managing collaboration with other groups at CSEM to make this system a reality. Then last year, we made 2 successful airborne field tests. And the most interesting discovery we found was the following. So we installed this sensor inside a helicopter in Denmark, and then we tried to measure the methane emission from cruising vessels in real time. And we were very surprised to find that the natural gas powered vessels and vessels transporting natural gas, they emit non-negligible amount of methane, which is not very good for global warming. And actually, this project was finished last year, but we are still working with this sensor temporarily for another European project, which is called the 3Rs. And then we try to monitor all major air pollutants and greenhouse gases simultaneously from a single measurement. And now let's move to this, the miniature microwave atomic clock. Mm-hmm. So, which is CSEM proprietary. So if you look at closely inside, you will see a millimeter size rubidium wafer cell, which is fabricated at the wafer level. And by using the laser interrogation and then hyperfine energy splitting of the rubidium atoms, you can control the 10 megahertz quartz oscillator with extremely high frequency stability. And the key advantage of this device is it is flat. It's only less than a 5 millimeter height. Why this feature is important? Because today, most portable devices, such as mobile and then global navigation satellite systems, they have a space, but they don't have a height, but they still need this tiny stable clock. And then the market potential is incredible. So coming back to the CSEM side, our group. So one of the biggest the advantage of CSEM is the very well established infrastructure for multidisciplinary research and development. Actually, the CSEM is covering all kinds of engineering areas, such as optics, photonics, and then electronics, precision mechanics, and even data science, such as artificial intelligence. So collaborating with other groups at CSEM, actually it creates significant synergies to reinforce our expertise on systems engineering, and also to develop more advanced and higher performance scientific instruments. That's all for today.
Thank you very much for that. It was really exciting to get the presentation. I didn't want to interrupt, but there is something for me very important, especially in the FLARE project, or every time that you're actually putting a laser in a satellite, or as you said, in a helicopter, scanning is an issue. Laser scanning is an issue, correct? And I understand that CSEM, which is very strong in MEMS and very strong in optics, maybe has very good ideas for doing the laser scanning. Let me introduce you to somebody. I have one of the most exciting companies in EPIC right now in the room. The company is from Itzehoe, Germany. It's called Augmented. So hello, good afternoon, Ulrich Hoffmann from Augmented. It's great to see you. You saw the challenge here. We have in the FLARE project, we have an infrared laser. They want to make an infrared sensor in one shot. So basically they are scanning an area. What challenge comes to your head? What kind of room for cooperation comes to your mind when you hear this?
Hello, Jose. Actually, I'm Bertolt Lange. I'm just the substitute for Ulrich, as he was not able to join today. Sorry about this. But hopefully I can answer the question. Actually, it's a pleasure to be with you live, first time in my life. And so Augmented is doing special kind of MEMS mirrors with some benefits in size and quality factor, as the LBS system is one of our most strongest targets. I'm really interested in knowing a little bit more about this laser systems. Actually, we are mainly interested in minimum dimensions. So form factor size is quite important, but also efficiency and power. So that's something where we should talk about.
Yeah. So basically, your main question was the light source. So the light source was a supercontinuum light source, which is not the COM source. But anyway, we tried to, it was kind of a optical fiber supercontinuum source. So basically, we seed at the 1.5 micron, and then we push it to a 3.5 micron, which because there is actually the methane, the fingerprint, and also the water, and also a bit further there is a CO2. And then the power, and then we designed the dispersion, and then the dispersion of optical fiber to confine optical power at 3.5 micron. So the power at 3.5 micron was about the 50 milliwatt, so average power. So if you see like 1 nanosecond pulse width and then 20 kilohertz repetition rate, you can calculate the peak power. So this was the laser. So the laser is outputting from the optical fiber. So the quality factor was pretty much nice. The most challenging part was the optics part, because we have to use the multi-pass cell, and then we had to design well the collimation. So
believe me, there is very clear room for cooperation here. And I think for the next stage, for the miniaturization of the scanning module, the two of you should work and talk, at least talk to each other. Yeah. Ulrich, sorry, Bert, thank you very much for joining today. And I want to go back now to Rolando, because I am a packaging guy and I can't wait. Packaging. Tell me what you do in packaging.
Thank you, Jose. Then let me introduce Stefan, who is Mr. Packaging at CSEM. And we'll talk to you about Stefan. Packaging integration.
Stefan and I know each other for 20 years. Stefan, packaging time. The floor is yours.
Yeah, thank you. So hello, everyone. So I'm Stefan Mordig. Moin moin to Itzehoe. So it's good to have someone here from Itzehoe. So this is where my ancestors are coming from before I came Swiss. But so the area at CSEM I'd like to bring to your attention is the field of microsystem assembly, or which is commonly known as packaging. So I guess every one of us is aware that any photonic component needs to be connected to the outside world to work at all. And often multiple functions need to be taken into account. So whether the component is active or passive, these functions can include optical, electrical, fluidic, biological, thermal, and mechanical aspects. And this is where we at CSEM are there to help SMEs and established companies to bridge the valley of death between inventing and commercializing. From design to prototyping, we have state-of-the-art processes like submicron assembly, flip chip bonding, adhesive, eutectic bonding, wire bonding, and so on. And also we have a dedicated clean room, which is not in Neuchâtel, which is in Altmark in Switzerland. So to carry out that work in a dedicated environment. The typical situation actually is that if an SME wants to get hand on their first prototypes, but they may not have the means to invest right away into a clean room or into all the packaging equipment needed, they can come to us. So I'd like to emphasize at this stage, so that it pays off to have close attention right at the start of a design to take volume production requirements into account. So this is in particular aggravated by the fact that a package often accounts for 60 to 80% of the cost of a product. So we are also a partner for more complex, beyond state-of-the-art solutions, where we have our own developments. And so Our focus is generically talking on affordable, compact, and hybrid solutions. And in particular, we're looking for harsh environments, thermal management, and hermetic packages.
So for me, one of the things every time I came to visit, it was the huge push for the space technologies that actually made you in position for reliability and robust hermetic packaging. And what I love now is that you brought those concepts into other application fields in which price and volume have been a challenge that you solved. So for me, this is fascinating. Show me what's on your hand right now.
So yeah, so this is I have brought with me 3 examples of quite diverse examples of product development which we have. So in my hand is a, I hope you can see it. It's a very tiny.
It looks like a match. Ah, yeah, laser source. Yes,
it's a laser source. So it's a medical device which has been used to illuminate the light in the human cochlea, and the tip of this sensor node includes a laser and a lens, which is packaged in a biocompatible housing, which includes sapphire and platinum wires. And it's in dimensions, it's very small. So it's less than a millimeter to fit in the human cochlea to stimulate the hearing nerves. So the key trick here is that we have developed a proprietary technology to hermetically seal also these components in sapphire. So coming to a much more heavier example like this one. Mm-hmm. This is a 160 watt laser package, which includes micro assembly of components. So submicron assembly is a key topic here. So we have a thermal management scheme, so with some water cooling inlets here, and it's a bench of 20 lasers, high power lasers, which is coupled to an optical fiber of 100 micron, which is not shown here in this demonstrator package. So the key topic here is thermal management and getting the heat out of the devices and micro system assembly. Now coming to the last type of device I have here. So this is a fancy looking type of device. So it's a medical instrument. It's a laparoscopic device, which has as a tip here an optomechanical probe, which at the same time as it puts pressure to the organs, measures the blood flow. That's a surgical device in the medical field. So we have obviously a connection to the outside world with some fancy algorithms to measure that correctly. So what we can actually see from all these devices, so in photonics, it's a world of quite diverse material systems. So we have indium phosphide, silicon, glass, polymers as materials. We have multiple wavelengths ranging from the UV to the far infrared. And this is why I believe heterogeneous integration is a key element to drive for the next years to come the development of research and developments in
Stefan, it was clear from Rolando in the beginning that you don't do production, that this is of course pushing the ideas into solving today's problems with key technologies. I would like to ask, is there a automation for packaging done or thought of, or how do you deal when you have a product that can be packaged and then you want to scale up or help other companies scale up to volume production?
Yeah, so this is what I was saying, that right from the beginning, we're starting discussing in the design, ideally already of the chip, to think about the volume production. And also actually, we're teaming up with equipment suppliers in various fields, so flip chip bonding and submicron assembly.
I brought you one here today. I brought you one. I actually brought the company from Berlin, and Stefan is German, so he likes Berlin. Andreas Schmidt from Finetech. Andreas, these people are really doing fantastic packaging solutions, and they want to partner with equipment suppliers to take them to volume. How do you feel about this? What kind of room for collaboration comes to your mind?
For sure. Thank you very much, Jose. Hello to CSEM, and thank you for the impressive presentation. I'm really impressed of all these photonic things because I'm coming more from the mechanical parts. So we know CSEM already, and we know they already have the machines to do packaging. We are interested in all this packaging solutions, and we can, or let's say we can build machines which are flexible in bonding technology, whatever it is.
Andreas, CSEM is very active now in the medical, is very active in quantum technologies, is bringing a new platform, as you just heard before, a new platform which Waveguide is below 1 micron in size. So packaging challenges are coming every day, and I love that the two of you can actually solve them together. When it comes to passive alignment, there is nothing more accurate than 0.3 micrometer accuracy of Finetech, unbeatable in this world.
That's true.
Andreas, so good to see you again. I'm going to come back to you later in the discussion. Stefan, thank you very much for that. I think Rolando wants to come back on the stage.
Yeah, maybe a short comment here. So actually, you were asking about with whom we're teaming up. And Finetech is is one of the companies, so where we have equipment to do also say the submicron and flip chip assembly, thermal compression bonding, and such kind of things. Yeah.
Thank you, Stefan. And jumping in back, and just to introduce the next colleague, Benjamin, who is coming from my group and is bringing you into the wonderful world, fabulous world of micro and nano optics. Benjamin.
Oh my God! You don't know. You know how excited I get when I hear micro optics, correct? Start shaking. Tell us, micro optics.
Hello, thank you, Jose. Thank you, Orlando, for the introduction. So yes, it's my job now to, in a couple of minutes, to tell you everything about nano and micro optics. So the job is it's quite something, but I will try my best. So as you know, in micro and nano optics, we are increasingly demanding in terms of specifications, performances, and also miniaturization. And all sorts of shapes now are required out of the design. But by chance also, we have tremendous achievements and progress in manufacturing. So all this together with our decades of experience at CSEM in micro and nano optics, we think we are ready to take the challenge. So I will talk first about micro optics. You know, now it's implementing, it's actually really booming. It's implemented in automotive, in lighting industries, and so on and so forth. What we do, we can address everything in the value chain, from design to prototyping to pre-pilot production. And we can also do UV imprint on chip in particular to serve prototyping needs. We can do on wafer or even to roll to play. I'll come to this later. And nowadays also we are facing a big trend in the freeform micro optics, right? It's a big keyword where we have micro optical elements which don't have any form of symmetry whatsoever. So as I said, for the value chain, we start first with design. Design is very important because we have to check for tolerances, manufacturability of the design, especially when we get to deal with very complicated shapes. I will show you here an example of a freeform tool we got to do recently. So this is a shim here with many different facets. It's actually a large shim, A3 sheet, and it displays really a nice optical effect. So I'm lighting up with my smartphone here, and you can see what kind of effects can be. So this is the tooling phase of our micro-optical manufacturing. And when we are done with tooling, then we have all sorts of prototyping, where, as I said, it can be UV replication on chip, on wafer, it can be rolled to plate, up to A3 sheets. And of course, then when this is done, we also have to look for characterization, and there we benefit from state-of-the-art characterization equipment to relate with design and the measured performance. And also we have integration and packaging. On top of that, we also have access to suppliers of specific materials of different refractive indexes and so on, which we can also use. Now I will talk about nano optics. Nano optics, as you know, it's the world of smaller structures. It's the size of the wavelength, or even smaller, can be deep sub-wavelengths when we talk about plasmonics and metasurfaces, for example. So before nano optics, and especially diffractive optics, was linked mostly to photonics instruments, but now it has been in the world of consumer electronics. So I will show you here a nice example of, well, I found really fascinating, and also the problem that for an optics engineer, I think it's really fascinating. So you know this product probably. It's an augmented reality device. It's the Microsoft HoloLens. And there is this piece where you have to bring light from the projector to the eyes of the user, and it's a diffractive waveguide. So actually we had some exchanges on this topic yesterday at the EPIC meeting on AR, right? So for those who have followed, you know what it is. So here we need to expand the eye pupil, and that's why we are using a waveguide, so that it's whatever the position of the eye is, we get an image. And it has to be transparent as an augmented reality device. So this is a really interesting piece of engineering, and we are active in this field of augmented reality waveguide. You can see here an example of our own. It's a diffractive waveguide in a refractive index above 1.9, 1.95. So it has actually the benefit of expanding the field of view from 35 degrees to 60 degrees with the same kind of limitations on the aspect ratio. So refractive index is a really hot topic in this field, and we are there.
It is quite a booming market. I actually for the nano optics or the meta lenses, this is something that is gonna come because of the whole thing you actually can make them. But I want to come back to the micro optics because I'm in Switzerland. I'm in the country of SUSA, CETRIS, IMT, LIMO, FISBA. I'm sorry if I forget some, but this is the boom area of micro optics in Europe, and you have been the spider in the web. One of the key markets that I have observed lately is the packaging of laser diodes, micro optics for the packaging of laser diodes. Actually, I have somebody from Focus Light in the room. Of course, Focus Light, the company that acquired Limo. Dirk Hauselt. Hello, good afternoon. We are in Switzerland. We are talking about micro optics. I can't be happier. Can you comment on this challenge today on the micro optics for the packaging of laser diodes?
Yeah, thank you, Jose. And Focuslight, at Focuslight, we produce optics and lasers. And of course, the challenge always is to bring the lasers and the optics together and with minimized amount of assembling steps, combining optics and mechanics functions in one element. And of course, the challenge is what production technology finally can be used to combine the mechanical and optical tasks together on wafer level. And especially, is it possible to optimize production technologies for the micro-optic structures and nano-optic structures to use finally advanced integrated circuit to wafer foundry technologies to make the wafer level optics, finally to bring the micro-optics on the next levels?
Dirk, that's a fabulous question. Correct, Rolando? Or yes, tell us.
Yes, exactly. Something, it's certainly a hot topic, and we are looking deeply into it. So we are collaborating with our colleague Amir, with whom you've had a presentation earlier, integrating together micro-optical elements on wafer and on photonic integrated circuits. So it's something we are really looking at. We are also integrating micro-optical elements on all sorts of VCSEL arrays, on SPAD imagers and so on. And there we have big constraints sometimes, which we try to tackle, but it's on a case-to-case basis, basically.
So
but
for an R&D center that is mastering the roll-to-roll, roll-to-plate, and also the replication, and at the same time also working with other partners on the 3D printing, it has to be very tough to know which is the right process for the right application. On that, I want to go to one of the market leaders. I actually had Genoptic in the room. I asked him to come because it was micro optics. Tim Lindsay, good afternoon.
Hi, good morning from the US.
Good morning from the US.
introduction.
Good afternoon here in Glasgow. I am quite amazed on how much micro-optics evolving in Switzerland, in Europe in general. How do you see the connection between Genoptic and the RTOs to bring those new processes to the volume production? Is that an easy way to collaborate?
Yeah, we're seeing a lot of requirements from our customers to make increasingly high mechanical precision to the micro-optic components at the wafer level or at the component level. So we are implementing a lot of really, really high mechanical precision for nearly passive alignment of structures to the laser diodes or to PIC devices or to detectors, whichever it might be.
Tim and Dirk joined the meeting today because they want to be part, as they are already, of course, of this new micro-optics revolution. And I want everyone to be part of it. Thank you very much for joining, Tim and Dirk. I will come back to you later in the Q&A. Back to you, Rolando Ferrini.
I'm coming back, Jose. Thanks, Benjamin. And then I'm introducing you the next colleague. For the housekeeping, we still have 2 domains to cover. So we start with sensing with my colleague, Christoph. Please, Christoph, the floor is yours.
Thank you very much.
Vision systems, correct?
Yep.
No, sensing.
Sensing systems.
Optical systems and sensing. Thank you very much for the introduction, Ronaldo. I'm very happy to be here. So my name is Christoph. On behalf of Stefano Cattaneo from CSEM Longport, I would like to introduce you the group of optical system and sensing. So CSM has a long track record in developing optical systems, customized optical systems, meaning the development of optics, mechanics, electronics from PCB to high-end ASIC design, but also the corresponding software from firmware to low-level or high-level software. These stuff can be realized either as OEM or standalone system, and this is thanks to the expertise that CSEM has in system engineering. Applications are, for example, if I name a few ones, are environmental monitoring, biochemical systems or sensor, counterfeiting measurement systems, or process monitoring system. Finally, I like to say the goal is not to replace consumer, let's say, scientific instruments, but rather to develop customized specific solution specifically for their needs, that we can really tackle their needs, what they want to, and produce this product or do a first prototype. And with this, I like to go over and show you a first prototype, or one of the prototypes that was done at CSM Longport. It's a fluorescence lifetime imaging camera. It's this one here. So a customer came to CSEM and asked him to develop a fluorescence lifetime imaging camera. Requirements were as small as possible, compact, and has to have everything included. Also, the calculation stuff has to be inside here. And this is what we came up. And to give you a short, let's say, physical functioning principle, how it works, fluorescence lifetime, that you know what we're talking about. So fluorescence lifetime, so you have a sample, you want to measure the fluorescence lifetime. The easiest means of understanding the physics behind it is you send a short pulse to your sample, and then you wait, and then you have the afterglow of the fluorescence lifetime. And with this afterglow, you measure the decay time, this tau, and this is the lifetime. And this is basically what this system does. And to show you a cross section, so here is the illumination path, basically this small pulse that comes out. It goes to the fluorescent sample in the front. Then we have here a fast optics with high NA to collect as much light as we can. And then down here is the whole electronics with FPGA and also a CSEM developed imaging sensor. And to show you what like a sample looks like, it's on this side here. So we have 4 samples on this side, or on this picture, 2 have the same lifetime. This is around 45 nanoseconds, and this is around 7 nanoseconds. And here, important is to keep in mind, this is not an intensity image. So it doesn't show you any intensity. If you put a normal photo on in the front here, you don't see anything. This is really every pixel determines the lifetime of the fluorescent sample. And this is why also, if you look at the samples here, they're not correctly homogeneous. So you see different lifetimes in the sample. You see almost 0 nanoseconds, all the way up to 50 nanoseconds. And with this, you get a nice lifetime imaging sensor. And to give you also some other perspective of products that were, or prototypes that were developed, here is one, a wound monitoring system where you can monitor a wound, then nanoparticle analysis. So this is called a MULS system, multi-angle light scattering system, to detect nanoparticles in liquid crystal. And the last one here, I have a liquid droplet detection system. This is a very fast system. It runs with about 20 kilohertz per second, the camera, and it can detect droplets down to about 10 nanoliters. And with this, I'm basically finished. I'd like to thank you very much for your attention and maybe waiting for some questions. Or
for me, what is incredible here is that you have managed to talk directly to companies and address their needs. Actually, I have very interesting company here with us in the room. I had the company all the way from Finland and China, I had the company iTechRec, which is a company that is bringing innovation from both sides and finding ways of working together. And Wei Li is here representing iTechRec. Wei, good afternoon.
Yeah, good afternoon.
Good afternoon. Wei, you came to this meeting trying to find new ideas for innovation. You came with a challenge, which is you're looking for a partnership on smart lighting for medical. And on that, this group is very strong. But in general, I would like to ask you, how can you help the innovation of CSEM? They have these medical products. How can you help them deploy them into the right customers?
Yes, now I'm working on the smart lighting for health. Yes, I'm interested in CSEM, the micro optics. Yes, so maybe in the future, I'd like to discuss with them about some optical components. Yes. Yeah, that would be very interesting. Yeah.
For the medical market, especially, correct?
Yeah. Thank you. Yes.
Thank you very much for joining. And I'm gonna come back to you in the Q&A. But I'm very impressed with the fluorescent measurement. I want to discuss this later. But before that, I want to, because I'm crazy guy about vision systems, and I was promised some vision systems. So Rolando Ferrini, let's talk vision.
Here I am, Jose.
Thank you very much.
Thank you.
Thank
Christoph.
you so much.
Last but not least, vision systems and CSEM story long 10 years, more than 10 years. And I give the floor to my colleague, Andrea. Andrea, floor is yours.
Ciao, Andrea. Hello.
Ciao. How are you doing? So thanks for inviting me here to speak about vision systems today. First, I want to say if there's one good thing that came out of COVID, it's having Jose do these events online, because they're really lively, and that's one of the benefits that happened. Vision systems have been happening for about 20 years at CSEM. And we know that vision systems are used almost in all industries today. And today they're particularly important because we mix vision systems with data-driven techniques and embedded machine learning in our group, and have done this for over 22 years. So it's not for us such a new thing. And our byline for the group is really to try to take the photon in and deliver information out on the systems that we make. And so I really thought the best way to explain how we do that is to actually just give you directly some examples of the vision systems that we make. So I start with a rather old vision system, which is called the Vision and Package. It's about the size of a sugar cube. And it contains really all the elements that we try to be expert on in our group, which is really the design of the optics. We also have a fabulous CMOS imager group that we have that can do imager design. Then we do the low-level boards and processing, and then also we do the communication. So this is really, and what we do in this actual unit at the moment is we do face detection. So it can actually be used to activate opening a door or something like this. And more recently, we look at eye gaze detection. And this allows us to look where people are looking if they're distracted. This has been a lot of uptake in the automotive industry as well as the aeronautics industry. The ones we use there are slightly bigger systems. We need a higher precision, but they came as a result of this. So that's the first one I wanted to mention. And then about 7 years with Ross Stanley, who's now gone and done his own startup called OptiRoss, we started making systems based on multispectral imaging. So trying again to simplify the hyperspectral imaging system down to multispectral imaging. And I show here another example. It's really based on Plan Optics 2. It's a very simple system that where we actually use the micro lenses, which we know is one of the key elements that offers Neuchâtel and the group also in Mutens here at CSEM. We use their micro lenses. And from that, we make a series of imagelets to give us a snapshot image of any device. This one's actually been used in looking at cookies or biscuits, as we say in England, and the biscuits as they cook and checking that the ovens go through the right way. And what's very nice about this very simple system is that we really only use the wavelengths and the bandwidths of the wavelengths that we need for the given application. So really simplifying the system to extract the information which is of importance. Another multispectral imaging system, which I think is interesting, is this one. It's called the Spectrox. And you were just talking about medical applications. This one's actually used for medical application. It's designed for looking at melanoma, so skin cancer. And the difference between this system and the previous system is the previous system, really you had a series of very small imagelets at each wavelength. So the resolution, the spatial resolution was low, but here now the spatial resolution is much higher. In fact, I don't know if you can see, but I tried to make a real demo, so I hope there's not too much demo effect there. But inside we use the full resolution of the imager, and then we have several LEDs looking out around the imager. And this allows us to have a good spatial resolution as well as a spectral resolution. We give up the pure snapshot, and it takes about 2 seconds to have an imager, to have an image on that. So this is the type of systems we're making. And I just want to talk about 2 final systems. This system is called the PUC. It stands for Plug, Use, and Collection Kit. And the idea behind the PUC is that it's really designed to help smaller companies start using data-driven techniques in vision. And we have a standard CMOS imager, 2 infrared imagers, and then we also have an array of microphones, a temperature sensor. And it's actually got just a series of magnets, thank you. Too much speaking French at the moment. A series of magnets. And what you can do is you can just stick it and then it will straight away do your data collection. And the good thing about this is that it's super simple to use, and it can be used directly with machine learning techniques or algorithms we've already embedded into the system, or it can be used to collect your data. Because one of the things that we've realized in working with companies is that you need a robust system. You often need more than one data source. And that's why we've made this collection kit, which actually collects many different data sources. And an example where we use this is actually looking in agriculture at pigs. So what we do is we look at the pigs moving around, and sometimes they break out into fights. Actually, it's not pleasant to see. It's called tail biting. And here with this system, we can do predictive if this is going to happen and separate the pigs before. And eventually what we hope to do, and we're working on now, is to actually remove the constant use of antibiotics in agriculture with this, by actually predicting if the pigs are going to need or get ill, and this way we can stop the use of the antibiotics. And then the final element I want to talk about, which is maybe the one which is closest to my heart, is sustainability. So we have a long tradition of making CMOS imagers, and inside this so-called unit is called Witness. It's actually a very ultra low power imager. It's a VGA imager that works at less than 1 milliwatt. And the idea is that it can be fed completely autonomously with this photovoltaic cell. And actually the idea was that it could be just a sort of plug and you can stick it on any wall. It's really a camera sticker. And from this, you can track people, the number of people in a room, so it can automatically tap in a type of IoT system to the heating of your house or such like, or you could have it perhaps as an emergency if someone's come out of hospital for a few days and you just want to check in case they fall over, and in which case you can really just stick it up, make sure your mom's okay for the next few days. So these are the type of image systems and vision systems that we've been working on over the last few years, and really excited to have had this opportunity to talk to you about it.
It's truly amazing. I am on this low power sensor that you have in your hand. Could you connect the detector unit?
So the detector here, it's really called the Ergo. It's a standard CMOS imager. The pixels are about 14 microns. It's a VGA imager, and it can work at 10 frames a second with a 1 milliwatt. So here, this is the imager. We designed it in-house at CSEM.
That's what I wanted you to comment on. So this is not a something off the shelf. This is a fully customized, designed by you and customized for you.
Exactly. We don't, we're fabless, so we go to one of the big players such as Towers or ST to make these type of devices for us, or LFoundry. But this is actually an imager that we designed in-house here at CSEM. And we actually have a history of low power imagers and ultra high speed imagers that we make at CSEM. And this is one such device. And we think that in the IoT revolution that's on the verge of coming, this hopefully will, autonomy and sustainability are two key issues that we want to move in. And also by treating the data locally at the edge here, one of the nice projects we're working on is a privacy dependent imager where we can pull out the key features of a face, but remove all the features that would make the face recognizable. And we do that in the optical domain and in front of our imager, which allows us to have perfectly privacy preserving IoT systems. So this is something else we've been working on a bit.
It's fascinating, Andrea, and we could talk also about the hyperspectral, which is also a very strong topic at CSEM, and we could talk about the agriculture part, and we could talk about so many things, but I want to finish with one thing. When it comes to the EPIC members, 750 companies, do you have a challenge for them on the detectors, or on the integration, or on the uncooled operation? Give us an item in your Santa Claus vision wish list.
So my wish list, I think, would still come from the multi-spectral imaging. And actually, it's maybe quite a big challenge, but it's a challenge that I hope that we can, as a community, work on. I think that we're limiting ourselves in multispectral imaging, and we're looking just at CMOS. And I think with the new materials coming out today on imagers, we should be looking beyond just using silicon as an absorption material. I think we should be able to push multispectral or hyperspectral imaging from X-ray to through visible, all the way to infrared.
Terahertz, yeah, the way there.
Terahertz.
Yeah.
And I think that we know that more data helps in the robustness and extracting the data of our system. And this idea today that we're stuck with using one sphere camera, one long wave infrared camera, one CMOS camera, I think we should be thinking a bit more outside of the box and say, why can we not on one chip make something that can really detect across the entire spectrum, and then we use and extract just the data that we want? And I think that this would simplify things in our community quite a lot, although making the actual device might be a bit complicated.
That's Andrea's challenge. From UV to terahertz, he wants to scan the whole wavelength range and will help you. But one thing that is moving a lot in the vision system is the mid-infrared segment, and that is something that's growing quite heavily. Is there any applications or any target list that you're looking at that wavelength range on the 3 to 12 micrometers?
Yeah, so we do actually, one of the nice things about the PlanOptics 2 system that I showed you is that they work very well in the new long wave infrared bolometers that are coming out. And the higher resolution of the long wave infrared bolometers allow us to use imagelets. And that's very important for gas detection at the moment. And there's been some nice, I think there's nice emitter work coming out. There's some exciting young companies like 4K MEMS who are looking at these emitters in the long wave infrared, and that's very important for gas detection, for air quality. And this is becoming an increasingly important part of our society today. A lot of people suffer from strong air pollution. And I think that the ability to give people a way to accurately measure the quality of their air is very important. And so pushing this barrier with the new bolometers, with the new IR glass that's coming out, This is allowing us to access previously a domain that was too expensive for the consumer market. So this is really exciting area to be in.
Thank you so much, Andrea, for this. And I would like now to thank, of course, all the speakers, but I want to go fast back to Rolando, because Rolando, this has been quite impressive. I have goosebumps. I mean, the lithium niobate is huge. The vision system that we just got, the fluorescence measurement, impressive. The FLARE project is one of the key projects in the ecosystem today. This is the micro optics region, and we got this as of course. It's me, it's micro optics, what I care the most. Everything was fascinating. What kind of answer to the epic question would you have? And don't say that was unexpected. What kind of room for cooperation do you see as the most important, the most urgent for you to start talking to companies about?
I think we need to have very much convincing use cases. So the technology is there. You can do marvelous things. You can do components. You can do devices. It's good to have, as Andrea was, for example, mentioning, to be in contact with the end user. It's also for the pilot lines. It's really the trigger point. You need to develop the right device for the right application. You can spend 10 years developing a nice device, but if afterwards it's far away from the application, you lose your money and your time.
Yeah, for me, what is, apart from the end user requests that are, of course, very important, we have collected many of those. For me, what is really important right now is to make sure that all the things that CSEM is doing in all the fields, from integrated photonics to micro optics, that they get exploited commercially. And on that, I am always super nervous, super concerned, but everything is on the right hands with you. But I really want to help. So we really want to make sure that all this innovation ends up in improving people's life and ends up in a valorization scheme. Do you see this as a challenge? Is it difficult sometimes for you to discuss with companies on how to take the finalized products to the next step?
The answer is not easy because it depends. It's case by case. So sometimes it's easy. I can tell you at CSEM we're able in 8 years to bring to the market as a product that nowadays you can buy an optical films containing the first free for micro-optical lenses the CSEM did. It was with a Swiss company here in the Basel region area, Regent Lighting, developing lighting luminaires. And there the discussion was easy because we were interacting with people talking the same language. It can be a bit more complicated if you have to interact, for example, with, if you have to have multidisciplinary, let's say, use cases where we have to discuss with doctors, we have to discuss with people in life science. There we speak very often the different language, so that for commercialization is to really understand what are their real needs, where we can really help with the technology.
You are making a difference in this industry. I am very happy to have you leading the fabulous pilot line, which is the most important pilot production enabled by the European Commission. Having you in the lead is a prize for Europe. And also I would like to say that as soon as I can, I'm coming to CSEM and I'm visiting all this in person because I want to ask everyone in the industry, travel. We need to get back together. This was Jose Pozo visiting CSEM, and that was Rolando Ferrini, the star, and all the speakers of Follow You. I would like to ask all the
stars are my colleagues, Jose, are all my colleagues.
All the audience right now, I would like to ask you if you could unmute your microphone, switch on your camera, and give the CSEM, the colleagues of Rolando Ferrini, a big applause.
Thank you.
Thank you.
And with this, I would like to say that this is it. Thank you so very much. And that concludes the public part of today's meeting. If you are in our Zoom room or informal private discussion,